concepts at the same time, and it's a lot to take in at the same time.
So I was supposed to take it this year, but then I was taking Calc 1 and 2, and then statistics, and then this class 1 with a bunch of other classes. I didn't want to do this at the same time.
Yeah, probably.
You're-
Like it would be horrible.
I'm gonna say you're probably gonna be a lot more prepared than what I was, because I've taken, so I took Calc 1 and 2, I've also taken statistics, but I've taken all of those like 4 years ago.
Okay.
So you're kind of coming still somewhat fresh off of that,
Yeah.
going into physics. A lot of this stuff, a lot of the concepts should at least still be similar.
Okay.
And I mean, like, for me, it's kind of still helped that I've taken those classes, but I feel like a lot of people do a lot better on those questions specifically because they have a little bit more of a fresher background. I would say, you know,
If
it's
we're
like one of those
going
things is
separately, do we still fill this out?
Yeah, because that's
You
the
can
labs
see
you can turn it in
relationships,
once
you
you
can
do it.
whereas, like,
Okay,
say,
got it.
Yeah.
And then also, I,
it's a little bit, it might be
because
harder.
I'm not gonna be here on Thursday, I'm not gonna be going to the trip, so are we gonna do the test for, or the quiz?
Oh, no quiz.
No quiz?
Yeah, because there's no
Okay.
class on Thursday, because
Okay,
we'll have
got
to
it.
drive.
Okay, got it, so I won't.
Watch it.
Got it.
You're good.
So, I know SMU, for I think a lot of their classes, they don't really require the calc base.
Yeah.
But I know OSU does. I don't know exactly what Washington has though.
If we're doing the alternate assignment, do we still pick up the field trip thing?
Yeah.
A bit of time, but my anxiety. Woo. It's a good way to bring it.
Let's go. Are you going on this?
Oh, great, you're going, Trent?
Yes. Are you going?
Oh, great.
He was going.
Yeah,
No.
I plan on it.
He was going. You were going? Okay.
No.
Hey,
I was not so sure about it.
You two should carpool then.
Don't tell your loved ones where you're gonna be. You know, the camps can get pretty dark, so.
Yeah, I already did, and they already told me to bring a jacket.
What?
They told me it gets cold.
Oh, yeah, it is cold.
That actually seems fun and I wanna go, but I have engineering stuff, so. No.
Boo. No.
Boo.
Thank you.
Boo engineering.
Boo, come to the cave with us.
What? My teacher killed me.
Marissa, do you have more waivers? I know it's super late in the game.
I can print them, yeah.
I wasn't gonna come, then I changed an appointment and I can go.
Yeah,
So,
sweet, yeah.
Yeah,
Yeah,
I can grab them after class or something.
Yeah,
Okay.
yeah, after class we'll sign them real quick.
Real quick. Okay, sweet, I'll grab them.
Yeah.
Good luck.
Trying to remember.
Yeah,
Ask
she's in it
my
right now,
fees.
so she should.
So, ask my fees. Those are like more like the shelf one guy, right?
Yeah, I
You're
think
also
the
your-
CEO are like the typical mushrooms.
I was trying to remember that because I know those two at least were like very.
I think Asco seats are like the cut.
I think they're the cup one guy. I think they're also
And
the.
or else.
Yeah, where else? That's another one too.
Yeah.
Sorry,
That's
I
why
was just like.
I got my paper on. That's my chemistry topic is involves mushrooms.
A specific
Psychedelic
level.
mushrooms, specific. Starts with a P.
Ends with Ivan.
Andrew, you have to, you know, it's a science experiment too.
Yes,
right?
it
So
is.
you gotta experiment with science.
Oh, I should do my own experiments, you mean?
Yeah, yeah, for science, for science.
I mean, you gotta test it out, right?
Hey, if anyone, yourself, at least, not some other creature.
I,
It'll be part of
Come
my,
on, go above and beyond.
it'll be
okay?
part of my discussion.
Yeah, well, Tori is talking about coffee, so I jokingly said that she should bring coffee samples, but you know, I shouldn't say the same to you.
I couldn't exactly do the same. That would go against RCC's drug policy, even if it is for research.
You cannot stop the science.
Yeah, come on.
That's happening in my body. We could be, yeah.
Is there lab today, or no, just trips?
Yeah, I'll talk about all that though.
I know, I love that.
Next week, then you'll be back making stuff. I don't remember what next week is, but
Glass and making chemicals.
yeah, I mean, we will be making aspirin pretty soon, so we'll be making aspirin pretty soon too. So.
It's probably not.
If we had an NMR that I would feel like better that we could test it, then I'd be like, yeah, you can taste it. But since we have like no way of getting to purity at all, yeah.
Yeah, whenever you're having your migraine, I think aspirin that we made in labs.
All right, happy Tuesday. So let's go over the week because we have a lot of things going on. And so just a reminder, right, we have our Oregon Caves trip. And so I need those field trip forms today, ideally. So I think I angry emailed some of y'all, so if you want to return those digitally, if I emailed you, because I just went off of the list of who said they were coming. But if you still need forms, as some people do, I can print them out and we can fill them in after class. And then, so that being said, right, there's no lab this week. And then go ahead and pick up the Oregon Caves field trip. So we'll go over what to do. And so if you're going on the trip, or if you're not, you can still do the field trip. So, you know, just a little bit of pre-lab questions. And then I put some information on Blackboard. So if you go to the content page, and then, sorry, let's back up. I don't like Blackboard. So if we go to content, week 6, and then for lab this week, there's a little bit of information. So we go to information, and so there's a few things about the geology that might be helpful, and also just to read and prepare yourself. So you can find information there. So that will help with your pre-lab questions. And then, so if you're not going on the field trip, so let's talk about the alternative assignment. So we have two options for the alternative assignment. And so basically kind of my options are traveling or no traveling. And so if you don't want to go anywhere, so no travel, then I'll ask you just to write 2 short essays. So if you go on the field trip, you have to write 1 essay just about the caves, how was it, blah, blah, blah. So I'm not looking to be too strict on there. If you don't travel, so write 2 short essays, so 1 page, and one of them will be on the caves, and then the other can be another geologically relevant site. Geologic. And so, right, I might say the Table Rock would be cool. You could also do, there are other like interesting things like the fisheries nearby. Yeah, Crater Lake. That's a good one. Even, what's the, like, Two-Vale Park? Like, anything that's cool, right? As long as it's relevant, you can write up the history, write where does the water come from. And then if you want to travel somewhere, so we'll do alt assignment with travel. And so, right, let's say the caves are too far for you, but you want to visit the Table Rock instead or something. So then you'd need to visit a site. You know, again, we'll say, i.e. Table Rock, since that's a lot shorter of a driving distance. Take a picture of yourself. So, right, we know that you traveled. And then you can just write one page on that geologically relevant site. And then you'll still do the pre-lab. So either way, right, you still have to do the pre-lab. It's just if you travel and want to see somewhere not the Oregon Caves, take a selfie, write one page over that. Otherwise, right, if you can't make it out to travel, read up about the caves and then read up on some other cool site in the area.
So is it one page for the no travel option, like one page for 2 essays, or just 2 pages for 2 essays?
Yeah, like 2 pages total, 1 page per essay. Does that make sense? So 1 page per essay. And then, of course, right, if you go to the caves on your own, that's fine as well. You just have to write 1 page. But again, please take a little selfie so I know you actually went. And then otherwise, you know, you can join us on Thursday. And so that also means, right, no class on Thursday since you'll be driving. And so if you're planning on coming with us to the caves, try to get there around 12:30 p.m., but we're saying probably 12:30 to 1 p.m. And again, let me know that you're going with your permission slip forms so I know who we're missing, so I know nobody drove off the cliff. And then carpool, if you want, right, that's probably good. It's a long drive. Anything else I need to say? Oh, no quiz then, obviously, right? So no quiz this week. There's also nothing to quiz you on since we just had our exam. All right, does that explain the Oregon Caves and all the permutations of combinations?
Yes, question, single space or double space on the essay?
We'll do double. We'll make it
Okay.
not torturous.
And then is there anything in particular you want us to address on the essay, or like?
I like to hear about, like, you know, how it was formed, if you can figure that out, when it was formed, geological age. If you're doing a river, right, what feeds into the river, kind of where does it flow to, that sort of thing.
Like what details about how they were geologically created, kind of?
Yeah, so anything about how it was created, or like, let's say you did the Tubal River, right, talk about what it's attached to, maybe what fish are there, what other local wildlife is there, that sort of thing. So it kind of depends, right? Or like, let's say you did the lava tubes that are more like in like East Oregon, then you could just write about how that was formed potentially and kind of, you know, the chemistry behind it, how it formed the tubes. So that sort of thing. And then posted on the Blackboard, so if you are traveling, make sure that you download directions, and then I would check this out because I would follow these directions because it says that GPS might lead you through a service road, and I mean, unless you have 4 wheels, you might not want to go that route. So I've made the drive before, and I just have like a Nissan Altima, so yeah, I think you'll be fine. I'm sure everybody has a much better car than I do for this sort of thing. But basically, you just drive to Cave Junction and then kind of keep going. And so again, you could follow those directions. I would download your maps. There's probably not a lot of service out there. Yeah, and then this is, so it mentions the last 10 miles to the Oregon Caves are narrow and winding. So just keep that in mind, that the last bit is a long drive. And then note they don't have charging stations to plug your electric vehicles, so just note that in your drive mileage.
Oh man, my Model S Tesla.
And then, yeah, be prepared for the tour. So it is pretty cold in a cave, right? I don't know you know that. So a cave is pretty temperature regulated, but that means it's pretty cold year round. So I would bring a hoodie at the very least. And good walking shoes, of course. It will be kind of slippery in there. And yeah, they have lights, and probably don't want to bring too cumbersome of things. There's no like crawling, but there'll be like crouching stuff. So we're not doing too intense of a hike. And then just make sure that if you do caving, make sure, right, that you haven't been in this area so we don't spread disease. So anywhere where you might have encountered the white nose fungus. And then leave your pets behind, unfortunately. All right, I think that's all about the Oregon caves. All right, so we went over, so no lab this week. But if you want to ask me questions, you can hound me today. And so that being said, I'm like 80% graded with the midterms. I just need to finish up the last 2 pages and add up the scores. So if you wanted to hover and hound me, I could probably get those graded during lab if you're interested. Otherwise, you'll see your scores posted. But as usual, right, I'm not looking to fail people, so just turn in all your assignments. We'll see how the grades kind of shake out. I haven't decided anything about, redos or blah, blah, blahs. But I'm inclined to not do that, but we can cross that bridge a little later. All right, let's go into your chapter, and we'll see how far we get today. And so we got a little taste of it last week in lab, all right? So we were saying, okay, well, we have electrochemistry, and basically, right, they started being able to isolate compounds, so making sodium and potassium and then other metals, right, strontium, barium, by electrochemistry. And so a couple of key things that we want to just take away from this is our unit conversions. And so we can see, right, our electrical energy, U, is given by our voltage and our charge. And so that's our joules. So that means, right, our units then is a joule is equal to a volt times a coulomb. But we might need some more useful information to help us with some of the problems. And so other conversion factors I would throw up here, and there's kind of 2. And so we have the charge of an electron. So the charge is, if we're in coulombs here, so that's 1.602 times 10 to the negative 19 coulombs. And so this would be useful, right, if we see problems talking about, well, how many like moles of something can you plate out? And we'll look at one of those examples. Yeah, negative 19, because this is one individual electron. Although that being said, so let's say you don't like this conversion factor. Let's put another one on there that is also relevant, if I can find it. Oh no. Oh, there we go. So we also have Faraday's constant. And so Faraday's constant is 96,485 coulombs per moles of electrons. So either way, so either if you want to work in units of moles of electrons or individual electrons, this will come up later. And so let's kind of keep orienting ourselves with our notes here. And so then we also have our relationship. So charge is equal to our I times our T. And so I is just our current. And so then we can multiply it by our time. And so this is just our summary of those relationships. And so let's look at a sample problem to see how we might apply these. So let's look at our book. So this is 25-1. And so the problem says a current of 1.5 amps. And so notice, right, amps is given up here what that is. So kind of just practicing our dimensional analysis. So flows for 5 minutes. Then what is the quantity of charge? So basically how many coulombs?
Can you post the live?
Oh, yeah. Oops. Okay, I posted the live on the main week 6 page. Oh. So I see answer in the chat, so let's go over it. And so again, right, this is just breaking down kind of our basic units and what we'll see. And so we're given, again, an amp is just a coulomb per second. And so we have to convert our 5 minutes. Now let's just start setting up our dimensional analysis. So 1.5 amps is flowing for 5 minutes, but we need to convert that to seconds. So 60 seconds in 1 minute. And so then we can multiply. And I think the answer in the chat is correct, but let me pull up my calculator. So 1.5 times 5 times 60. And so we got 450 coulombs. And so kind of the idea is then we could relate this to quantity. And so let's actually skip to your homework for a second, because we could figure this out just by our dimensional analysis. And so let's skip down to number 4 on the second page of the homework. And so think about what we just went over. So we went over some conversion factors, right? So either moles of electrons or individual electrons. We're talking about amps here, right? It's saying, well, how much current do we need? And then think about the reaction that's going on, right? We're going from copper 2+ to copper 0. So how many electrons is that? And what else do we need? So I'll let you think about it for a little bit. So what are some thoughts? What did you guys think to calculate, or what are some relationships that we need?
I might be wrong in kind of thinking this, but, well, first off, I kind of figured that I would change the grams of copper into moles of copper. And then technically, because our relationship is for the Faraday's constant, it's for moles of electrons. And we know that we need 2 electrons per, say, 2 electrons per atom of copper. I had an equivalency of 2 moles of electrons per mole of copper.
All right, that
Kind of
looks
fine for Faraday.
that looks good. Sorry, I'm just stopping you for a second. So let me catch up, because that's correct. Or at least a good starting point. So, right, let's do that. So we have 5 grams of copper. We said, well, let's convert to moles. So 1 mole, so about 63.55 grams. And so, yeah, just like you said, it's also 2 equivalents, so that's the other thing to note. So that's why I said, right, pay attention to your oxidation states, because if you do this again, right, it could be 3 electrons transferred, 1 electron, so you have to look at how many electrons. So let's do that, so times 2. So for 2 moles of electron for every 1 mole of copper. And then, so where do we go from there? Let's punch that in. So times 2. So now this is how many moles of electrons, right? So what should we do with this number now? I think you had mentioned our Faraday's relationship.
So, because our Faraday's relationship is 96,483 coulombs per moles of electrons. So, that should be, I think, another conversion right there.
Yeah, so that sounds good, right? Because we want to figure out basically how many coulombs we need. And so then this is telling us, okay, for every mole of electrons, it's 96,485 coulombs, which will then, of course, get us back to our time, because we need to figure out total coulombs first. 485. So now that's our total coulombs. And then we said, okay, well, we have a 1.17 amp. And what were the units of amps?
Coulombs per second.
So coulombs per second. And then we have 1.17 amps, which is coulombs per second. So if we divide by that, right, that'll give us seconds. So divide by 1.17 to figure out how long we have to run it. And so I get that many seconds. So now I'll write that number down. So 12,976 seconds. And then, of course, we can convert it to minutes or hours. So divide it by 60. So 216 minutes, or divided by 60, so 3.6 hours. Questions about that one, how to kind of walk through that process? So it's all just keeping track of your units as well. All right, so we're going to flip back to kind of our lecture slide. And so that's kind of our quick electrochemistry summary, again, right, thinking back to what we did in last lab where we're actually applying a potential to something, right, forcing a reaction to occur. And so now let's kind of look at what we're studying, because we're kind of looking at two different things, but basically we're going to switch to focusing on the galvanic cell. And so, right, electrochemistry is just defined as the study of these redox reactions that either produce or require an electric current. And so kind of the big picture, what we're trying to get at is either if they require an electric current, right, these are not spontaneous. And again, hence why they have to be driven forward. It's also how we mine metals, though, out of the earth and what they started doing, right, initially back in the day, that if we apply an electrical current to our salt, we can get out all our molten metals. But we're going to kind of, again, shift focus to our galvanic cell. So those are going to be spontaneous reactions that, again, are driven forward chemically. And we've gotten a taste of that, and I'll remind us of, once again, of that copper sulfate and zinc reaction, right, where the zinc replaces the copper, so that's spontaneous. And so, right, we can use those half reactions to power a cell. And so conversion between chemical energy and electrical energy is carried out in an electrochemical cell. And so this goes back to the very basic, battery that you can kind of make with a penny and hook it up, or like, the lemon juice batteries, anything like that would be an electrochemical cell. And then, you can even think about kind of the research that's going on now into figuring out like better ionic liquids and all sorts of things, right? So trying to figure out, how do you make those batteries more efficient? How do you make that electrochemical process occur, and then of course occur reversibly, right? Because then you want to be able to apply the electrical charge once it's all spent up, and then perfectly, regenerate your battery, basically. So that's kind of, also what leads to battery life and all that once you, again, get into it. And so again, we're going to kind of be focusing on the galvanic cell, also known as the voltaic cell. I'll generally use the term galvanic to describe that. So again, looking at chemically driven spontaneous reactions. And so like we mentioned and saw last week, right, so those non-spontaneous redox reactions, if we figure that out mathematically, then of course you have to apply electrical energy. All right, so let's look at our spontaneous reaction once again. So we're just kind of zooming in. And so let's identify, so who's being oxidized, who's being reduced here? Zinc oxidized. Copper reduced, excellent. And so we could also separate those into, right, their half reactions. So zinc solid gives us zinc 2+ plus 2 electrons, right? So again, oxidized, so losing those electrons. And then our copper, of course, writing its half reaction, so copper, forgot, plus 2 electrons gives us our copper solid. And so we'll just kind of zoom in on that. So we'll see it again in the cell, but you can kind of see what's going on, right? We have our zinc, it's losing electrons, so it's supplying those electrons, right? And then the copper 2+ in solution can pick that up, and then of course, right, deposit, which is what you've seen before. So you've seen this reaction. And so just recapping some terms. So again, we went over our electrical current, so how much electric charge that passes through a point. So either as electrons or ions. And then, right, we've been identifying our redox reactions, so that's just kind of continuing from last chapter. And again, identifying the movement and how many, so I'll just kind of put that right, so how many electrons. And so kind of think about that right when you balance your half reactions. It's just, you have to have your electrons balanced. And again, right, a spontaneous redox reaction does not require external energy like a battery. And so we'll eventually get to, right, calculating our delta G, so that's kind of coming up, and also how it relates to the cell potential. And so again, like we've been saying, our galvanic cells, which is basically a battery, produce electrical current from our spontaneous reactions. And so now this goes into kind of our setup of the electrochemical cell, right? And so this is just our initial, well, what's a good reaction, right? What's a good system here? So this is spontaneous. But now how do we take that system and make it into an electrochemical cell? And so it kind of guides us through that process. And so the oxidation reduction reactions are kept in separate little half cells. And let's scroll down so we can look at our picture. And so they have little beakers. And so again, note, so now let's think about our half reactions. So we said zinc was undergoing oxidation. And so there's, right, our zinc metal and then our zinc solution. So we have to have some ions in solution. And then we have our salt bridge, so ions can flow through. And then, of course, right, we have to complete the circuit, so we just have our anode here, which we'll get to explaining in a second. So our anode, so that's connected to our zinc metal. Then electrons are flowing from our anode to our cathode. So I just don't want to go too fast. And so just going back to our words, okay, we saw they have their separate cells, so each little beaker. Or again, right, in a battery, you would have to think about how do you have those separate little cells in such a small battery. And then, of course, right, we have to have a circuit. So again, electrons flow through that wire. And we have to have a conductive solid electrode. And so again, we can think back to last week. That's why we were using the little pencils and trying to shave them, since graphite is a decent electrode. And so that last part is, again, we have to have an exchange of ions with our salt bridge. And so now let's look at the different parts. And so this is important. So at our anode, and you can remember because it starts with a vowel, that's where oxidation occurs. And again, right, let's go back to it. And so we can see in our galvanic cell, okay, right, we have our anode, oxidation is occurring, and again, right, electrons are being formed at our anode. And so this is why our electrons, again, flow right from our anode to our cathode over here. And so again, we can see, right, we have our copper, so our copper metal, and then it needs those electrons being supplied so it can convert our copper nitrate to copper metal. And then you can appreciate the zoomed in picture at least. And so the anode is connected to the positive end of the battery in the electrolytic cell. So that was a little confusing if we remember right from lab. So a little bit of convention sign difference. So that's the electrolytic versus the galvanic cell. And then so our anode, so in our electrolytic cell, it's going to be losing weight. So it's, again, being converted from our solid to our ions. So, of course, it's going to be getting smaller. So you could quantify that as well if you could measure that, really well. And then our cathode, so two consonants. So cathode is always where the reduction occurs. And then our cations are attracted to it. And then, of course, it would be gaining weight then, since it's plating on be copper. So any questions just about the basic cell setup? And so again, just kind of helpful reminders if we need to calculate things. We also have an amp defined as 6.242 times 10 to the 18 electrons per second, so other unit conversions if you find that helpful. Probably the Faraday's constant will be better. And then the amount of force that pushes the electrons through is called our electromotive force, or EMF. And so we already defined those. And then, so the next question is really, right, our cell potential, and how do we know if it's spontaneous or not spontaneous? And so it says, right, our difference in potential energy between our anode and our cathode is then our cell potential. And so, right, it depends on basically the ease at which the oxidizing agent is reduced at the cathode and the reducing agent is oxidized at the anode. And so again, right, you can kind of think back to lab for this. And then, so this is also important. So when we talk about our standard potentials, this is all for standard conditions, so 25 degrees Celsius, 1 ATM, and 1 molarity. And so we will talk about treating this in non-standard conditions, but this could, of course, right, lead to a little bit of deviation in what you see in real life versus theoretically. And so let's kind of go through then how we know our reduction potentials. Thought I had. So this is, sorry, I was looking for the formula. Now I can't find it. So this is kind of the formula, but I don't like this formula because I think it's kind of confusing. And so, right, it says that your cell potential can be done by you take your cathode minus your anode, but it's a lot easier just to kind of add, right, your reduction potentials, and then you just kind of flip the sign. And so let's go into what I mean by that. And so again, we want to look at our little cell here. So we want to figure out, right, how do we know if it's spontaneous? And so we've kind of, again, got a taste of it. So I'm looking for my standard reduction potentials. And so again, right, these are all reduction potentials. And so how favorable it is to add electrons to it. So things that are most favorable are up top. But then if you wanted to do, right, the opposite reaction, so let's say you were doing the oxidation, right, so going from 2 fluorides to producing our fluorine, then we can just flip our reaction, and then that flips the sign of our electron volts. And so basically, the math, so we say, right, our cell potential for our redox, for reduction, is equal to, right, our negative of our oxidation, which I believe we explored last week in lab. And so then let's, again, apply that to our cell here and just kind of verify what's going on. And so we have, again, our 2 half reactions. So we said we have our oxidation reaction of our zinc becoming zinc 2+, and making 2 electrons. And so then we go to our reduction potential chart. And where is zinc? And so, right, we look down here, but it's the opposite, right? Because this is the reduction potential, but we said zinc is getting oxidized. And so we could either kind of rewrite this or copy this for a second. And so let's just say, just so we're really clear, so from our table, right, we can read off, well, it's zinc 2 plus 2 electrons gives us zinc solid, and that has a negative 0.76 volts. So if we want to flip it, right, I'll just rewrite it, and so that flips our sign. And so now it's plus 0.76 volts. And so now that's, again, our oxidation potential. So I'm just going to rewrite that. So 0.76 volts for that reaction. And then we can add it to our copper reduction potential. So let's get that from our chart. Where's copper? Copper. So copper is 0.34. And so that's what we want, right? The reduction reaction. And so now we can just copy that. So copper 2 plus 2 electrons gives us our copper solid. And so that's 0.34 for its reduction potential. And then for our cell potential, right now we can just add our 2 appropriate half reactions, which is easier than trying to remember which way to minus things. And so then we get our cell potential is 0.76 plus 0.34, so 1.1 volts. And so this is telling us that it's spontaneous since it is positive. But again, we'll keep looking at that relationship. Yeah, sorry, that's like an equal sign, equals. That didn't come out very well.
So if the cell potential is positive, you said that means that the reaction is spontaneous.
Yeah,
But it would be flipped with the Gibbs energy.
you're right, yeah. So we'll get there, but yeah, Gibbs should be negative and this is positive. Yeah, confusing.
Pay attention to signs.
And so now let's look at how we abbreviate them. And so what I mean by that is we have our little cell diagram shorthand. I was trying to find an example. Well, let's just write it for this one. And so you'll see this either on an exam or on the textbooks. It lists out this shorthand, and so we just want to be able to translate, right, what does this mean, and how do we write it shorthand, and vice versa. So again, our same cell diagram. And so the general rule is you have these 2 lines, so this is your big separation, and so that separates your oxidation. And so your oxidation usually goes on the left side, and again, right, the anode is where oxidation occurs, and then reduction is put on the right side, so remember RR, so reduction, right side, and then our cathode. And then in there we will need to specify kind of more detail, and so let's look at that. And so we need to say, right, what our oxidation reactions are. So our oxidation, again, we said that was the zinc, and then so you lay it out with your metals on the outside, so we have zinc solid, and then one single line represents, then this is our solution, so our zinc nitrate. Then you put the double line to again signify, right, this is our oxidation side versus our reduction side. And then now the copper nitrate goes next, so kind of the way to think about it is your solid metals should be on the outside of your cell diagram. And then, are we okay with this one? And so let's look at a little bit different scenario. And so typically, again, when we set up kind of these cell diagrams, and just like we did up here, right, that we had our anode is made of some metal that is oxidized, and the cathode is the same metal that is produced by reduction. So that's kind of the simple standard case. But sometimes you have a redox reaction that involves the reduction of an ion to a different state. And in this case, you may use an inert electrode. And so that would be either like a carbon electrode or platinum. Can't remember if palladium is also used. And again, your inert electrode does not participate in the reaction, but is just a surface to provide transfer. And so let's scoot, my notes flew away. And so we just want to compare the cell notation. So let's kind of first orient ourselves and examine what's going on. And so our oxidation side is pretty standard, right? So we have our iron metal is providing our electrons. So it's getting oxidized. And then if we check out, right, our reduction side, well, this is the problem. So we have this permanganate species, right, MnO4 minus, and it is undergoing reduction, right, to manganese 2 plus. So we can see we're going from 7 to 2 plus. But these are both soluble species, right? So we can tell that they have the little AQ there. They're both ions. So they're not landing, right? There's not magnesium metal that they're able to land and exchange on. So that's how we know we need our inert electrode. So in this case, they pick platinum. And so now let's compare the cell notation. So again, pretty similar. So we have our metal, right, electrode part, so iron, and then our iron solution, double lines to separate, right, oxidation versus reduction. And then notice it lists out, right, your two species. So your previously, right, 7 plus form, then the reduced form, acidic conditions, and then line electrode. So you still have that line that separates out your electrode. And again, right, could see glassy carbon as well. So just kind of be aware for that statement of, right, it would have to say an inert electrode, and it will tell you what that inert electrode is. All right, let's take a little break. That's a good spot for a break. So we'll come back in 10 minutes. I'll probably grab some field trip forms. Did I send you? Oh, maybe you didn't sign up. Okay, because I only email people that sign up. I can put one down.
I don't think it ever got.
I held it out and Kabrina grabbed it before you
Make sure to bring food. I think it's at least like 2 hours. Oh,
there.
yeah, I might hang out longer than just an
Makes
hour.
sense.
Like,
It's called like what if hiking snow. I don't know. I'm not the biggest fan. But anyways, he filmed it. Yeah.
that hiking trail road.
Yeah, I'm next to it. And it's right there. Like they just shut down the whole park.
I know.
My friend and I,
I could waste like a year to get a shot.
before the road, her and I never been used to real talk for other dollars. We never put $5. We were like, it's burgers night. We thought about going to the rocks. To Oregon.
Are they actually from Decatur? Is that what you-
No.
Probably not.
No, because it's all big.
Yeah, yeah.
And then
Yeah.
there's the one in Redmond, which was like last year and the year before, but that's where we talked.
Maybe when they were like.
That one, that, yeah.
They took all the cool stuff out.
But they left there.
That's cool.
Oh, it looks like my lineup, it would be Zach Bryan, Cody Johnson. Jesse Green.
I am now the exact opposite human being. I just haven't told you how 100% of the time. I'm like, I'm outside, really effort. So I'm like, I need too much sun. I'm afraid of the sun.
This term might be better.
Oh my God. My birthday, my friend. My birthday, not your birthday.
Yeah, we got. There's one that's smaller and one that's a bit bigger.
And then she talked to
This
me.
is not, but
Yeah, since the last time you talked to him, he said that you got it.
this week.
Oh.
You want the form?
Yeah, I think I appreciate
As long as you're not under 18.
I know, that's the fear. My friend, she was born in Italy, my sister, but she went on like summer trip with like friends and like things like that. And then they started dating. And while they were like, she was
It's based on the way she wants what I actually
and then they were dating.
well, no, cause I don't wanna go.
And then we were like, now we have and Lex was serious. I don't know. We're already kind of going through this. No, but she made that. This was like September when we bought the ticket. And then she just went and.
Yeah. How far have you gone?
I won't be able to go to the field trip or engineering trip. I pushed back a day, so I won't be able to go this Thursday. I don't blame Portland, it's all their fault.
Yeah, I do blame them.
But alternatively, I think I'll probably end up just going to Phoenix and their group on a different day.
That sounds fine.
Where am I going? Friends in Phoenix will get me mad over this week. We'll see. But thank you for being understanding.
Taking your own car?
I'm wondering, because I usually have something to do with each other. Yeah, I know. I don't know if I'll make it out of the way, but.
Oh.
But it was just kind of weird.
Yeah, basically,
Well, it's gonna take Bree to read. She's riding the bus. But yeah, it should be fun.
Barely outside.
oh, yeah.
One right here.
Oh, yeah, yes, please. Thank you.
Can I have a peek at how I did on the test or after?
Yeah,
Lecture?
yeah, after the lecture.
Okay.
Are we back from break?
Go out of this building and then walk down the street.
I know the preference.
I'll know how to get
Now let's come back to lecture.
Order.
I know, do I need a gavel? All right, so the next thing we're kind of doing, and so all this lays out is kind of like how we got these reduction potentials. And so this kind of goes back to like research now, like if you made a new compound, well, how would you determine the reduction potential? And so the secret is you can't just, do a reduction potential basically, right? So the absolute tendency cannot be measured. So what this is saying is we have to compare it relative to another reaction or another electrode. So this is often called, right, that we have to have our standard electrode or a reference. And so that also means, right, you do your little experiment and then you do it with a known compound. So usually like ferrocene, if you were doing organometallic chemistry and trying to figure out new reduction potentials. But basically, right, we have to compare it to something. And so we've kind of set then our standard potential. And so we have, right, our reduction of H to H2 is a sign then of 0 volts. So that's just our standard hydrogen electrode potential. And so everything is, again, compared to this reaction. And so again, right, our standard hydrogen electrode is again defined to be 0, so everything is compared to that. So whether it's harder or easier to reduce, again, relative to this reaction, so that's all you're comparing it to. And so, right, half reactions with a stronger tendency towards reduction than the standard hydrogen electrode have a positive value. And then, of course, anything with a stronger tendency towards oxidation has a negative value for our reduction potential. And so again, we can kind of see that, right? So looking at the bottom, so I always kind of say orient yourself. So we have at the bottom, so these are our reducing agents, so they spell it out for you. And of course, right, these are our oxidation reactions, so very negative potentials. So right, they want to give up electrons, and so that would be a much more favorable potential if it was reversed. And so like we saw again, right, our oxidation is also equal to our negative reduction potential. So I encourage you to flip the signs with the reactions. And then again, right, orient yourself. Our oxidizing agents are on top. So like fluorine is a strong oxidizer. And peroxide, so that makes sense. And so this is where I think it's kind of confusing how they try to explain the math. So again, I encourage you to look at your standard reduction potential and then again flip the value accordingly. So what they've done here, and we can walk through it, so they're just comparing, right, the zinc to our standard potential. But notice that they wrote down, right, the voltage for the other half reaction. So they wrote down the negative voltage, so going right in this direction from our zinc 2+, so the oxidation reaction. And then they did their formula of minusing it, where you do cathode minus the anode. Again, I find that confusing. I think it's a lot clearer if we just rewrite our voltage, right, as 0.76 for this reaction. Again, reversing from this table, right? So then now that zinc gives us zinc 2+ plus 2 electrons at positive 0.76. So that's the only thing that I would say to kind of watch out, because they like to use that subtraction convention, but I find it more confusing.
No one wants more negative sides.
Yeah. And so then we can kind of compare. So again, you want the more negative thing at your anode. And so this is just kind of comparing your reduction potentials. So right, if you have, let's go back to zinc versus, where was the copper? Copper, right? So zinc is lower, so this is a more favorable anode where the oxidation is occurring. So that's kind of your other trick is, again, right, the more negative thing needs to be the anode. So that kind of helps you tell if it's spontaneous, but I much prefer still to just kind of do the math, right? Write out the two half reactions, get the potentials, and add them. And so blah, blah, blah. So we have to have a large positive half cell potential. And then again, electrons flow from our anode to the cathode. Again, just a reminder that, right, our oxidation reaction produces electrons, and so they flow. And so there is showing, if we measured this with a voltmeter, we should get that reduction potential that we were expecting. So again, comparing to our standard hydrogen now. And so they've written our oxidation reaction, and their little voltmeter is showing 0.76, which is what we expect, right? Again, based off of our chart and flipping these signs. So that is a much better way to do it. And so again, which way will electrons flow? So there, again, just kind of comparing our reduction potentials. Kind of the other way that I encourage you is kind of, right, compare the opposite reaction. And this could be a good technique, like let's say you're given a scenario and you're trying to figure out, well, who should be the anode, who should be the cathode. But you just want to compare basically your two different scenarios. And so what if we did the opposite, right? So what if copper instead was supplying our electrons? But we can already see, right, that's not looking too favorable. So copper gives us copper 2 plus 2 electrons. And so that is negative 0.34 volts. And then compare that to our zinc reaction. So zinc, let's say it was being reduced. So now it has negative 0.76 volts. Sorry. Point, negative, just so you can tell. Sorry, it's hard to tell what I'm writing. And so just to be clear, right, that's negative 0.76 volts. So now our total potential for the opposite reaction is negative 1.10 volts, right? And so our negative number, not spontaneous. So now this is telling us, oops, well, copper, right, cannot be my anode, right? It can't be supplying the electrons. This doesn't work out spontaneously. So I don't know if that kind of helps. Yeah, I think their method is confusing. So now they're just trying to compare, right, oxidation potentials, but I think it's better to compare the half reactions. And so this is kind of, right, the hint, but again, I always say just do the math. So I'll say that, do the math of half reactions, right? That's the most reliable way. So this helps you. But just in case, right, you get confused, just go back, do the math, add your half reactions. And so, right, we said a redox reaction will be spontaneous if, again, our oxidizing agent wants to be reduced and a reducing agent wants to be oxidized. And so if it is higher on the table, right, it has a strong tendency to be reduced, and lower tends to be oxidized. So again, kind of what we were saying with our metals. So again, they end up being oxidized. All right, so now we're starting to get into our delta G a little. And so like we've been saying, so right, when our E cell potential is positive, then our redox reaction is spontaneous. And so we'll relate it back to delta G. Delta G will be negative, so just, right, remember that from our free energy chapter. And, oh, we have a typo, and then when our E cell is negative, the reaction will be non-spontaneous, and delta G will be positive, sorry, the typo on those notes. All right, so blah, 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 right, we have our standard reduction potential table. So hang on to that. And so then, right, we were calculating our cell potentials. And so this is kind of interesting, right? So let's look at this part because this is a little confusing. And so our cell potentials are intensive properties. And so that means, right, that it does not depend on the quantity. So we do not multiply the half cell values even if we need to multiply the half reactions to balance the redox equation. So a little confusing, right? Because we just took an exam, and again, you'll get those back. If you want to hang around, I can grade them. But most people did pretty well on the balancing equation, the half reaction problem. But I did notice some people went really astray if they did not balance the redox reaction. But then, right, we can't get confused because now we're just looking at our potentials. So it doesn't matter, right, if the electrons don't match now when we're determining our kind of cell potential. So it's kind of more position related is what I like to think about it, kind of like a waterfall, right? So not so much amount, which is kind of confusing. And so blah, blah, blah. They have their formula. I don't like to use the formula because then I'll get confused and I'll mess it up. So I just add the half reactions. So I'll just add that in there. So again, add half reactions with correct sign. Otherwise, right, that's how you use the formula. But if I try to explain it, I'll probably do it wrong. All right, so see if you can figure this out. If I need to flip to the cell potential page, I can. And so now we're trying to figure out, right, what's our standard cell potential. So kind of break down your half reactions and see what you can determine. So what are our two half reactions?
The first one I did was the oxidation of aluminum.
So aluminum solid goes to aluminum 3 plus 3 electrons, and then let's see, so let's find that on our sheet. And so that looks like negative 1.66, but then we're going the other way, so 1.66.
Do you know what page that table's on in the textbook? Because there's a smaller table in chapter 25, but it doesn't have the nitrogen half reaction on it.
Is there another reduction table in the back? I want to say it's like D, but I don't have the page, unfortunately. So then the other one, this one was a little tricky. If we could find it. I think it's on this page. I'm not sure if it's in the one I gave you. I hope so. Otherwise, I'll have to print you more.
It looks like they also have it in the appendix.
Oh, nice. Do you want to give us the page number for the appendix?
It's A-36, there's no page.
Oh, so A36, I'll put that at least. And so it should be, I believe, this one. So we have the NO, or nitrate, and then acidic conditions, we can go back, right? Nitrate plus 4 protons gives us NO, and water.
The only difference is that it has one more significant digit. It's like 0.9579, not 396.
0.95,
Textbook is,
0.9576, you said?
just 0.957.
0.957, I'll just put that on the side there. That's funny. And so that's going in the correct direction, so we don't need to change the sign. And so now I'm just going to rewrite that. So nitrate plus our protons gives us NO plus 2 equivalents of water. So that was, again, 0.96 or 0.957. And so then we can add our reduction potentials. So 1.66 plus 0.96 or so. And so we get our cell potential of 2.62 volts. So no questions on this one. And so again, we'll keep going. So like we've been saying, right, if we have our positive reduction potential, then it's going to be chemically spontaneous. Again, we have seen this with our zinc copper one a million times now. And then of course, right, we saw that this would be non-spontaneous, so we could potentially force it with our, again, battery reactions. And so go ahead and practice for these. Although, you know, if you want to calculate the E cell, I would say go ahead, because it might be easier to calculate just your E cell potential. But figure out which one of these would be spontaneous, not spontaneous. And then if it is spontaneous, we can practice making our little sketch. So let's take a look at A, and we could try to do what they suggest, right? So see if we can not calculate the E cell. And so what we would do is just compare iron and magnesium, sorry. And so let's look. So we have magnesium down here, iron up here. So magnesium is lower. So if magnesium is lower, right, this one should be oxidized. So it should be the one supplying the electrons. So that's already kind of a hint that this probably isn't spontaneous, right? Because it's the opposite, so it's the higher one. But again, I don't always like just looking at trends, so I like adding up the numbers just to feel good about everything. And so what did you get for the reduction potential of iron solid to iron 2+?
Negative 1.93 volts.
Oh, for the whole process?
Oh, yeah, my bad. So for the iron, I got positive 0.440 volts.
440. And then if we go magnesium 2+ to magnesium solid, what's?
I got negative 2.370 volts.
So that looks good. So did everybody get at least somewhat similar values? So you might have a difference in the hundredths place with some rounding. But yes, right, so now we're just double checking with the math. So we said, okay, well, magnesium probably should be the anode, right? It should be the one undergoing oxidation since it was lower. But then the math just helps us reaffirm that. And so, right, we got that negative number. So whoops, probably set up backwards, right? So if we flip this, that would probably be favorable, right? And so we could say, well, could flip setup, right? So magnesium needs to be oxidized or reducing agent, right? Whatever term we want to use, or the anode. So now we have a bunch of different things to say, right? So either magnesium should be the one oxidized, or basically, right, it needs to be the metal at the anode. And so what about the next setup? And again, let's just look at it without the math, so kind of practice. And so now we're comparing iron and lead. So again, look at your reduction potentials and who is lower. So I see iron, oh, and there's lead. So iron is below it, so that's already kind of a good sign, but again, I like to do the math. And so now if we do, so iron solid to iron 2+ plus 2 electrons. So what's the reduction potential on that?
Same thing that we had before, the
Oh.
0.440 volts.
So 0.440. And then now we have lead 2+ plus our 2 electrons gives us lead solid. And what's that?
I got negative 0.126.
Negative 0.126. And so then what do we get for our overall potential?
0.321.
So 0.321.
Oh, I used a slightly different value for the iron one.
Okay, because I was looking, I had like a 0.314, so that's probably that.
Oh, I got 304. What did you say you got?
I got 0.314.
0.314. What did you get, Andrew?
I used 0.447 for the iron from the text. It had
And then
447, so I got 0.321.
And I was using the handout that you gave us before, so
They're all
that's probably why it's
slightly
different.
variable.
Okay. So any sort of permutation, combination, so somewhere right around 0.3. So we're already seeing, right, values will vary, that's fine, but that looks good there. So, right, positive, still spontaneous, so that's nice as well.
Would it be valid just looking at it qualitatively to see too that magnesium in the activity series would be higher than iron? So you could say, oh, iron most likely isn't going to displace
Yeah,
Like,
that's
you see, like,
another,
that's probably not
yeah.
spontaneous.
Yeah, that's another good way to look at it. So yeah, you could go back to the activity series. So lots of different ways to kind of think about it. I just always go back to like the math and the reduction potentials since it can get kind of confusing. What are we talking about? But yeah, other great way. And then the other thing to just practice, so it said, right, make our sketch. So then, right, can you do that? So kind of practicing. Well, we said iron is our anode, so let's put that on this side. And we are making iron metal. And so that's the other thing to kind of look at with these electrochemical cells is make sure you don't have a tricky situation with a glassy electrode or platinum. And so, right, just kind of identify, oh, yes, we do have appropriate metal surfaces to work on for this reaction. And then on an exam, right, just kind of label it your iron, put Fe2 plus in solution. Let me move my picture down. And then don't forget, right, all the parts of your little electrochemical cell. So show some sort of light bulb connected in there. Show your flow of the electrons, right? So electrons are produced there. Show them going over to our cathode. And you probably want to label, right, anode. And then now hook it up to our cathode. So now our lead solid that goes into our lead solution of lead 2 plus floating around. And then don't forget, right, your salt bridge. And then we could also label this our negative end or positive end. So just being able to do that. Questions on drawing this?
Can you do the shorthand version?
It depends what it's asking for. So yeah, an exam could ask you, you know, for the shorthand, it might ask you to translate shorthand to like a full cell diagram. Because that's the key point that I'll be looking for is like, you know, do you have the salt bridge? Do you have the correct flow of electrons? Because those details aren't in the shorthand. All right, so then kind of the next part goes along with the idea of our activity series. Oh, sorry,
I
question?
do have a question, not specifically with the diagram itself, but kind of with the reaction. So, because it doesn't really matter on, say, it doesn't matter on like, say, molarity or concentration, that it's going to be that 2.4 volts, or sorry, whichever amount that it is.
So no, we're just talking about standard conditions. So
Okay,
one
gotcha.
molarity. So we will,
Okay.
I think we have a formula coming
I
up.
was curious about that, because I was like, you know, I didn't see a lot when it came to like molarity. I wasn't sure if it was
Yeah.
more moles or less, because I was like, how do you increase voltage? But okay.
No, we'll talk about, yeah, how to calculate it with different molarities. But yeah, right now we're just focusing standard condition, 1 molar, yeah.
Gotcha.
So yeah, right now we have the blinders on, kind of standard conditions. And so then, again, you brought up the point we could think of the activity series, and so this is exactly right what this is related to. So you can think back to your lab and what you saw, and right, so you saw most metals dissolve in acids, although pretty slowly, right? So the magnesium was fast, and I think the zinc was maybe dissolving really slowly. And that's represented by this reaction, right? Zinc dissolving in acid, but from what I remember, that's a pretty slow time scale already. And then I think y'all read the fun fact of, right, how the guy dissolved his metal when the Nazis were coming in aqua regia, so he had a nice gold solution. And so that is, again, pretty standard practice, is making the aqua regia. And yeah, so this is aqua regia. And it should be in a 3-to-1 ratio, they just don't have that there. And again, right, safety tips, you can't make and store aqua regia long-term, so it's not really stable. Eventually it can, if it, yeah, I'm kind of curious, so I'm assuming if you just dissolve like the gold in aqua regia, that must be pretty stable. And so this didn't happen to me, but another grad student that I know, like one day they were just, happily at their fume hood, explosion went off, they didn't know what the heck happened, and it turns out someone had like some waste container of aqua regia solution that they were saving, which like you would absolutely not do. So if you were using aqua regia for cleaning, you finish cleaning and then you neutralize it right away. And you don't want to store nitric acid solutions either, because nitric acid and waste can make horrible things that could potentially explode. So yeah, it must just have been that gold was pretty stable, so that's how that Nobel Prize guy was able to store it. I've always wondered about that one. But yeah, other impurities could cause that to explode. And luckily the grad student was fine, but that was, no one likes a random explosion.
Only planned explosion.
Yeah, only planned explosion. And so again, right, you can refer to the reduction potentials to help guide you. Can't find our standard reduction potential, there it is. And so right, copper is above it, so copper, remember, right, doesn't dissolve in acid, so pretty inert, same thing. Silver just kind of looks at you.
I have a question about the salt bridge, and so its purpose is it's just a channel for electrons to travel?
Yeah, and like ions to keep exchanging through, yeah, because you got to keep the flow going of everything.
Okay, but it's typically not like the constituent ions, like the example in the book is like you have one where it's potassium chloride, but then it's with the in zinc and copper solution.
Yeah, it's just like any salts can pass through it is the idea. So any ions are passing through. So yeah, could be
It could be the
random
same,
ones,
yeah.
or we typically think of the ones in solution, but they probably added the potassium ones to get better like conductivity anyways. All right, so that is, all right, so now what y'all have been waiting for, the moment. How do we go from our cell potential to G and, oh, don't forget good old K again. Yeah, and it's K not for Kelvin, but for equilibrium, right? Good old equilibrium comes back to haunt us once more. And so now this is, I don't know what you want to call this, right? Our little power triangle. No, I just made that up right now. Yeah, our Triforce, delta G, power triangle. And so now this is just giving us, right, all the relationships, so everything we need to know. And so our delta G then is equal to our negative, so number of moles, so we'll break this down, right? So now this would be number of moles that are involved in that transfer, right, for that reaction. And then multiplied by our Faraday's constant once again. And so that's relating our cell potential and then going back to delta G. So write that down, Faraday's constant. And then, so then of course, right, we can go from delta G back to K, or we also have this formula where our cell potential is equal to 0.0592 volts over N, so right, number of moles again, times our log of K, so times our equilibrium constant. So I'd probably write down these formulas somewhere, they'll be useful. And then if you need to write these things down as well, right, write them down, because we've talked about a lot of different conditions. And so this is just a recap. So right, we said Gibbs free energy has to be negative, so we have to have available energy to do our reaction, to do work. And then, right, E cell though, that's positive. Same thing with our equilibrium, right? It generally has to be greater than 1, showing that it's going in the spontaneous forward direction. So we'll just add that right forward direction, since we're generally talking about our forward direction when we're examining our spontaneity.
What is F up there,
Yeah, so back to that Faraday's constant. So again, write down your Faraday's constant if you haven't already. All right, so now you can try this reaction. So see if you can figure out, so start with the cell potential, of course, and then figure out whether it's spontaneous. So how are we doing? So I went ahead and at least kind of calculated the E cell potentials. So did we get this far at least? And might have some discrepancy. So adding our two half reactions, so we get negative 0.53 volts or so.
That's what I got as well.
Excellent.
That's all I've done.
Oh, sorry. And then, so we'll go through it. I was hoping to finish the chapter today, which is why I'm trying to rush y'all a little. So then we have our negative, delta G equals negative NF E cell. And then how many electrons were involved in this process? How many? Sorry. Well, just So you're just looking, yeah, because it's just 2, right? Because it's 2 were formed and then 2 were consumed. So, right, our N equals 2. And so now we can just plug it in. So equals -2 times our Faraday's constant, so 96,485 coulombs per mole times our 0.53, so that's joules per coulomb, right, for our E cell potential. So that's just what volts is equal to. Yeah, and then what do we get for, oh, right, negative, your, good catch. So then multiply everything. And so then we should get positive, and now we're in joules. So I like it, so 102,000 joules. But that's a big fat plus sign, right? So now we could already tell from our cell potential, but now this is just re-verifying, right, that this is non-spontaneous. All right, let's skip this one. Well, let's practice the next one. So now let's see, well, how would you calculate K? And now we have the oxidation of copper by H+. Don't forget that standard reduction potential. So for time's sake, I'm just trying to go over this. And so again, right, set up your half potential. So this one we said was our standard reduction, so it's 0. We can double check our copper reaction. So where's copper? Oh, now I can't find it. So 0.34, except then, right, you have to flip the sign since we're going copper solid to give us electrons. And then we get our cell potential, right, is -0.34 volts. So probably, right, not spontaneous, but let's go ahead and calculate our K. And so, right, this is just from our other formula, so our E cell potential is equal to 0.0592 over N times our log of K. And so N is 2 again. And then just start plugging it in. So negative 0.34 is equal to 0.0592 over 2 times our log of K. And so now just algebra. So let's solve this. So divided by 2, so negative 0.34 divided by that. And so now I get something of negative 11.48 is equal to our log of K. So take 10 to the power of both of those things. And so now we get our K of 3.26 times 10 to the negative 12, which roughly makes sense, right? Because we said it was negative, so we expect, right, a pretty small K equilibrium constant since not much is being formed. So that looks good. All right, let's try to at least kind of rush through the last section just so we've at least kind of talked about it. And then, like I said, will be available. I'll go sit in lab now, and if you have questions about this homework or anything, you can bug me. And so the last little bit is, well, what happens if we're not at our standard cell potential? And so this is just going through the derivation of the Nernst equation, so going through this relationship and substituting in for our delta G here. And so I would just go ahead again and just highlight this. So this is useful. And so blah, blah, blah. So we have, and then this simplifies. So you also might want to highlight this because this is really the better form of our cells. So and now let's recalculate what this is saying. And so basically this is saying for our non-standard cell, this is equal to our standard cell potential that we calculate at 1 molarity minus our 0.0592 volts over N, so N's just moles, times our ln Q. And so now, right, this is saying, so kind of going through, so blah, 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 we can still get a spontaneous reaction when our oxidation and reduction reactions are the same as long as our electrolyte concentrations are different. So this is kind of interesting. And so this is due to the entropic difference in our solutions. And so electrons tend to flow from our less concentrated solution to the more concentrated. And then, so now this is kind of showing, right, the phenomenon. So first, just our standard cell, 1 molar, nothing happens. But now if we increase it to 2 molar and 0.01 molarity, now we have a standard. Oops. And so if we have, sorry, I didn't copy this question over. So determine the cell potential for a cell based on the following conditions. So we have oxidation is copper, goes to copper 2+, and it's a 0.01 molarity solution, 2 electrons. And reduction MnO4 plus 4H plus 3 electrons. All right, we'll probably have to stop there since we're over time. So I'll probably just continue this on Tuesday then, because I don't want to rush it any more than I'm already kind of rushing this. And so we'll see how to plug in, but basically what you do is you solve for Q going back to your equilibrium expression. But we'll go over this again on Tuesday, but if you want to stick around, we can talk about it more. So don't forget field trips, forms. And I got yours online, so you're fine. Anybody else last minute field trip?